Good afternoon, folks. How are you today? We are in week number 8. Last week, we started talking about curve fitting. So let's take a look at curve fitting. So our problem is we are given n data points. That means we are given xy coordinates of points that we have numbered 1 through n. And we are also given a fitting function, which is of the form c1 times some function of x plus c2 times some function of x, so on and so forth. We say this function is linearized because y is linear with respect to c1, with respect to c2. So our c1 through cm are our unknown constants. So our dependent variable is linear with respect to these unknown constants. So what we want to do is we want to find their best values. What do we mean by best? Best in the sense that these values should be unique and the curve should minimize deviation from the data points. So if we fit some kind of a curve here, we are defining our deviations to be vertical deviations. And then last week we looked at various criteria and we found out there are two criteria. One is called minimax criteria, which we did not go over further, and the other one was least squares criteria, which is the one we implemented. So we said if we take sum of the squares of vertical deviations and we minimize them with respect to the C1 through Cm, we get our least squares method. And then we did a matrix formulation. In this matrix formulation, we said all we need to do is we need to tabulate these functions. So we are given x, we are given y, and we are given these functions f1, f2, fm. So we evaluate these functions. These are functions of x. We know x, so we know these functions. So therefore, we now have a y matrix, n by 1, and we have a function matrix, f, n by m. So in our matrix formulation, we know both of these. So if we know f, we can take its transpose. So we know our transpose is going to be m by n. So we know y, we know f. Since we know f, we know f transpose. So we can multiply these two. So we will get a matrix A m by m, C m by 1. Again, we know both of these. Multiply, we will get a matrix B. So now we know A and B, we want to find C. And we know if we are going to use computers, we are going to use matrix inverse. So we know C is going to be inverse of A, which is also m by m times B. So that is going to be our formulation. So then in the last lecture, I did a very simple example. I fitted a straight line. So I was given 4 data points, and our straight line is C1 times 1. So our first function is 1 plus C2 times x. So C1 is our intercept and C2 is our slope. So F2 is x. Since x are 1, 2, 3, 4, we did 1, 2, 3, 4. And then I did this on a piece of paper, even though it looks like as if I'm doing it on a Excel spreadsheet. We should really do properly in Excel spreadsheet, and that's what I'm going to show you next. But just to let you know, in case you think we are just fitting a straight line, we are not. Let's take a little more complex example. This was our fitted straight line. So here is our example, very practical one. It's an example from wind tunnel, force and velocity. I don't think this experiment is done anymore. An object is suspended in a wind tunnel and the force F is measured for various levels of wind velocity V. So what we want to do is we want to fit the following curve. Y is C1 times X. So notice it is linear in C1. C2 times X square, linear in C2, even though the function itself is nonlinear. C3 times e to the minus x, again y is linear with respect to C3. E minus x is definitely a transcendental function. So our x's represent velocity in meters per second. We have 5 data points. And y represents force in newtons. So before we move on, let's see if when we are coding it in spreadsheet, instead of going through all these steps, can we write them apart? So you can see C is equal to A inverse times B. So we will need to multiply inverse. So we would like to take inverse of A. Now A is F transpose times F. So A is matrix multiply of transpose of F by F. So that would close this parenthesis. That would close this parenthesis. So we have got M inverse of A. And then we want to multiply it by B, which is matrix multiply of transpose of F times Y. So close this parenthesis, and then we will close this parenthesis. So that must be our formula, right? Let's see, we'll apply it. So I'm going to fire up my Excel. So I've got a blank worksheet, and for the time being, I'm not going to spend the time talking about formatting and all that. So let's see, we have X, we have Y, we have 3 functions, F1, F2, and F3. Okay, our F values are 10, 20, 30, 40, 50. Y 25, 70, 380, 550, 610. Okay, our first function is equal to x. Our second function is equal to x squared. Our third function is equal to e to the minus x. And notice, this is all the work I need to do. I'm going to now just copy all these formulas down. I'm going to name my matrices. So I'm going to call it, first let me box it and name it. So we are going to call it Y matrix. This is our function matrix, so box it. We'll call it function matrix. And that's it. So now we are going to calculate C, which is a 3x1 matrix. And remember our formula. We are going to matrix multiply inverse of A, which itself is matrix multiply of transpose of F by F. So let's close parenthesis, comma, matrix B, which is matrix multiply of transpose of F by Y, close parenthesis here, close here, Control Shift Enter. And we have got these C1, C2, C3 values, right? So let's box it. And we can call it, we can't call it C, so let's call it CC. Okay. So now if we want to have what is Y of the curve, so remember it is C1 times F1, C2 times F2, and so on and so forth. So all we are doing is we are doing matrix multiply. So we'll do matrix multiply first row by CC. But it'll be a single value. So I just hit enter, copy this formula down, and this is our Y of curve. So now what we can do is we can plot X, Y, and Y of curve. So we are going to go insert an XY chart. Let's say we want data and smooth curve. So this is our curve. And we can of course fix it by showing you which one is curve. The orange one is curve, blue is our data. So I'm going to show it to you in my slides. So these are our blue data points and red is our curve. Right? So you saw how easy it was. Just on a fly, within 5 minutes, I fitted a curve, fairly complex curve, to our data points. Now I could have had hundreds of data points here. It wouldn't have mattered. Our formulation would have been easy, straightforward. Okay, so now that we know how to fit a linearized curve, let's look at fitting non-linear curves. So what do we mean by a non-linear fitting function or non-linear curves? So as an example, let's suppose we are given UV data. So this is an exponential curve. So our data is U versus V. We are given n data points. The reason this is non-linear is while V is linear with respect to K1, V is non-linear with respect to K2. So we say therefore this fitting function is non-linear. Remember we had Y which was linear with respect to C1, with respect to C2, C3, that was a linearized curve. So before I move on how we solve these kind of problems, this is going to be our generic response. So what we will be is we'll be given a problem in nonlinear world. So in this nonlinear world, our problem is u, v is given, our fitting function is given. So what we are going to do is we are going to transform this. So we are going to transform this into a linear world. So in linear world, we will transform this data to xy form. And this nonlinear equation, this exponential curve, will become linearized here after transformation. Then we are going to solve. So in this case, let's say we are doing curve fitting. We are going to solve and we are going to find C1 through Cn. Once we do that, we will do an inverse transformation. Once we do inverse transformation, we will get K1, K2, K3, so on. So basically we have solved this problem. And then we just need to validate, verify, validate, etc. That indeed our solution makes sense. So if you're taking a course, say, where you have done Laplace transforms, that's what they are used for. Basically, you use Laplace transforms to solve a nonlinear problem. So you're given a problem, you take a Laplace transform, you solve it there, and then you take an inverse transform, and that's your solution to nonlinear problem. So our transformation methods don't need to be unique, and they depend on the nonlinear problem. So let's look at our exponential curve. So we have V is K1 times exp of minus K2 times X. Oh, times U, sorry. So our data is U. So what we do is we take log of both sides. So when we take log of both sides, we'll get log V is log K1 minus K2 times U. So what we do is we define log V as same as Y, log K1 same as C1, minus K2 as C2, and U as X. So our equation will become Y is C1 times 1 plus C2 times X. So you can see this is our linearized form. So this is linearized, and this was our nonlinear form. So in nonlinear world, we are given u and v, want to find k1 and k2. After transformation, we have in linear world x and y and this linearized fitting function to fit. So once we find C1, C2, we know K1 would be therefore e to the power C1 and K2 would be minus C2. So that's what we are going to do. Okay. So we are given a bunch of data points, U and V. So this is a problem about intensity of radiation. So let's suppose there is some kind of radioactive radiation. As you know, the intensity is going to fall off exponentially with time. So we want to fit a curve, something like intensity of radiation versus time is K1 E minus K2 T. So if you are given T versus I data, so we have T versus intensity data. So notice what we did was we took log of V, that became our Y. So we'll take log of I, that would be our Y. Then our first function would be just 1. Our second function is x. X is same as u, which is same as t. Remember, this is u, this is v. Right? So if we were given all this, we can find all this. We know all this. This is our function matrix. This is our y matrix. We can solve for C1 and C2. Right? Once we do that, we calculate K1 is e to the C1 and K2 is minus C2. That's all we need to do. Okay, let's look at another curve. This curve is called power curve. So in power curve, we are given V is K1 times U to the power K2. So even though this is linear with K1, V is not linear with respect to K2. So again, we try taking log of both sides. Log V is log K1 plus K2 times log of U. So again, we call this Y. Let's call this C1. Let's call this C2. And let's call this X. So our equation will become Y is C1 plus C2X. So again, this is our linearized form of this power curve, right? So once we find C1 and C2, K1 would be just e to the power C1 and K2 would be same as C2, right? Let's do an example. So here is a power curve. This is from a chemical reaction rate versus concentration. So you might have seen examples like this in chemistry, where if you keep on increasing the concentration, you expect the reaction rate to change, but then eventually taper out. So this is our data. Doesn't look like a great fit. So maybe it is not a good description of this chemical reaction. But nevertheless, so we have chemical reaction rate, gamma, is K1 times concentration, which is like U, to power K2. So again, remember, we are given concentration, that's same as U. We are given reaction rate, which is same as V. And log of V is our Y. So we take log of this. And then our two functions are, first function is 1 and second function is x, but then x is log of U. So we'll take log of this. So log of V is Y, log of U is X. So again, we have Y matrix, we have F matrix, we find C1, we find C2, and then we do an inverse transform. K1 is e to the C1 and K2 is C2. And we plot them. So we plot the curve K1 times concentration to the power K2. So our green dots are our data points, blue is our fitted curve. So you can see it doesn't fit very, very well. Okay, let's see another example. So next curve is called surge curve. So here we have V is K1 times U to the power K2. So notice power curve times exponential of minus K3 times U. So it's power and exponential curve combined. Now notice what will happen when we take log of both sides. We'll get log V is log K1 plus K2 times log of U minus K3 times U. So again, we define this as Y, this is C1, this is C2, this is our F2. Let's define, let's move this minus sign inside. So we'll move this inside like that. So this we'll call C3 and this is our F3. Okay, of course, F1 is equal to 1. So once we find C1, C2, C3, we will know K1 is e to the C1, K2 is just C2, and K3 is just C3, right? Okay, so let's see an example. So this is an example from one of your labs that you might do, similar to it. So we have concrete, and as you know, when you mix water into concrete, it strengthens, but you have to be careful. Too much water and it won't be strong enough. Too little water, it won't be strong enough. So we fit a curve like this. So here, our x-axis is percent water, which is U, and y-axis is strength, which is V. So we are given this data points. So U percent water, V is strength, right? So when we take log of V, we will get Y. So we take log of this. This is our V, we'll get Y. So F1 is 1. F2 is log of U. And F3 is just minus U. So we have all this. If we have this data, we take log of V, we have our y-axis, and we have this functions, right? So once we have y-axis functions, we can find C1, C2, C3 using our least squares technique. And once we find C1, C2, C3, we know K1, K2, K3, and we can plot this curve, right? So you can see blue dots, very nice curve fit. So this is a very nice description of strength of concrete versus water. All right, let's do one more example. So this is called saturation growth curve. So here we have our V versus U. So you can see V is linear with respect to K1, but not with respect to K2. Now, if we take log of both sides, we can't really separate out K1 and K2. That is what we are doing. So what we'll do is we'll invert the two sides. So we'll write 1 over V will become K2 over K1U plus U over K1U. So we will just get 1 over K1. So we'll define this as our Y. We'll define 1 over U to be our X. So this will become C1 and this is our C2 times 1. So our equation is Y is C1 times X plus C2 times 1. So again, once we solve for C1 and C2, we will get K1, which is 1 over C2. And since K2 over K1 was C1, we know therefore K2 is C1 over C2. C1 times K1 is C1 over C2. All right, let's look at an example. So we have data points and the curve looks something like this. So again, we have U versus V data, right? So we define our Y, which is 1 over V. Our F1, which is equal to X, is 1 over U. So we take 1 over U, and our F2 is just 1. So again, we have our Y, we have our F matrix. We solve for C1, C2, and this is how we'll get K1 and K2. Okay. So we'll do this. Okay, let's do an example. So we want to fit the surge curve to the following stress strain data from compression test of a concrete cylinder. Now, I'm sure all of you have taken the strength of materials lab or even material science lab. And remember what you did in material science or strength lab, you did a tension test. So you took a cylinder and you stretched it. Here what we are going to do is we want to test compressive strength of concrete. So we'll take a concrete block and apply force on it. So we are going to measure stress versus strain. So we have stress strain data here. Okay, so remember what was our surge curve? Let's go back. So this was our surge curve. Remember, it had a power component and it had an exponential component. Right? So when we linearized it, our y was log v, our f1 was 1, f2 was log u, and f3 is minus u. Right? And then we got k1 was e to the c1, k2 was same as c2, k3 was same as c3. All right. So let me fire up Excel. And again, we are not going to be concerned about all our formatting and all that. So U, V, U, V. Okay. By doing it online like this, I'm trying to show you also how quick it is. So let's make sure we have 6 digits. Okay. So 2250, 3575, 4250, 4400, 4200. Okay. So remember our y is log v. So we'll do log of v. Okay, and then our f1 is just 1. f2 is log u. And f3 is minus u. All right, so let's do equal to 1 equal to log of u equal to minus u. Okay, take all these formulas, copy them down, right? And this is our y matrix, so let's name it y matrix. This is our f matrix. Let's name it f matrix. And we are going to find our c's. So remember, we have 3 c's. Matrix multiply of matrix inverse of matrix multiply of transpose of F by F, comma, matrix, did I do it close? Matrix multiply of transpose of F by Y. Control Shift Enter. So what do you know? These are C's. So from C's we get K1, K2, K3. So here is our K1, EXP of C1. Here is our K2, and here is our K3. Right? So we can name them. So let's name them K underscore 1. I can't name them K like that. K1, otherwise it'll be a cell name. K underscore 2. And let's name this K underscore 3. Right? So now we can get V of the curve. V curve. So our V curve is going to be K underscore 1 times the power part, U to the power K underscore 2 times the exponential part minus K underscore 3 times U. Okay, so we just copy this down. And now we can plot these U, V, and V curve, right? Okay, so let's see what we'll see. So this is what I have done, and this is our curve fit. So notice, beautiful curve fit of compressive stress strain curve. Okay,